Let's look at another example of a related rates problem. In example 2, I have an observer that stands 300 feet from the launch site of a hot air balloon at an elevation equal to the elevation of the launch site. So I have an observer, I've got a person over here that is looking at the launch of a hot air balloon. And this person, they tell me, is 300 feet away from the launch site. So this side I'll call x is equal to 300. The balloon is launched vertically, so what does that mean? The balloon is moving straight upwards. So this side right here, right, if I think about this as a right triangle, is moving straight upwards. It's going vertically. So it's launched vertically and maintains a constant upward velocity of 20 feet per second. So I see this number, this 20 feet per second. I know that's describing how the balloon, how high the balloon is from the ground. How about I call this side over here y? And now the thing I don't know about this 20 perhaps is, does that 20 represent y? Or does that 20 represent the derivative dy over dt? And you can look at the arrow that I've drawn here. You might be able to conclude that this is actually describing dy over dt. It's talking about the rate of change of this side. But in case you didn't see that, the thing I would point out is this rate right here, this 20 feet per second. In particular, it's a velocity or a speed. Anytime you see a velocity or a speed or a rate of change, any sort of rate, see feet per second, miles per gallon, something like that, that's a rate of change, that's a derivative. So dy dt is 20, and I know that it's a positive 20, because think about what's happening. The balloon is moving upward, so later on the balloon's going to be way up here. This side has gotten longer, so my derivative should be positive. So dy dt is 20. What else do we know? It says, what is the rate of change of the angle of elevation of the balloon when it is 400 feet from the ground? So the balloon is 400 feet from the ground. What is this angle of elevation nonsense? Well, here they give us this hint. It says the angle of elevation is the angle theta between the observer's line of sight to the balloon, so that's this person looking at the balloon, that's their line of sight, and the ground. It's the angle created by those two sides. So that means that this right here is my theta. I actually just created a little right triangle. And we'll see right triangles pop up a lot in this section, just because right triangles have a lot of neat relationships that we can utilize when we're writing equations. So okay, I've got just about everything laid out. The one thing I would say is, well, what are we trying to solve for? What are we looking for? It says, what is the rate of change of the angle of elevation to the balloon? What's the rate of change of theta, of this guy right here? In other words, what is d theta dt? I don't know. So I don't know d theta dt, but that's okay because that's what I'm going to try and find. I don't know theta. I actually could go and find theta. We actually have the tools to find theta, but I'm going to come back to that in just a little bit and say let's worry about that later on. We've got everything over here on that side. We don't know what dx over dt is, but let's see if we can figure that out. What's happening is this is the main side that's changing right here. This is what I want to think about. My balloon right here is just going straight up. So how is that affecting this side of my triangle right here? Is that side of my triangle, is this bottom side getting longer or is it getting shorter? And of course you would tell me, well, that's a trick question. This side right here is not changing. If it's not getting longer, if it's not getting shorter, the derivative of that side must be 0. So dx over dt must be 0. So I have almost everything I need. The only thing I don't have is this theta. Again, we're going to come back to that. Some of these problems you can solve without having every single little piece. So just because I don't have theta doesn't necessarily mean it's a problem. We'll come back to it if it is. That's fine. Let's see. What do I want next? I want a relationship. I want a relationship between theta, y, and x. In other words, I want a relationship between this angle, its opposite side, and its adjacent side. Angle, opposite, adjacent. I hope you are thinking what I'm thinking, and you're thinking about tangent. I know that tangent of theta is equal to its opposite side, which is y, over its adjacent side is x. Now, I could go and just take the derivative with respect to time, and there's nothing to stop me from doing that. That's fine. But the right-hand side in particular, this y over x, would pose somewhat of a problem. We could deal with it. It would just mean that we'd have a quotient rule. But if I have the choice between doing the quotient rule and not doing the quotient rule, I'm going to choose not to do the quotient rule pretty much every single time. So how am I going to do that? I'm going to look back at my picture over here. And in particular, I'm going to draw my attention to this piece right here, dx dt. If you have a side that is not changing, so in this case, dx over dt is equal to 0, what I can do is I can take that side length, and I can plug it into my equation before I take the derivative. So I can take x equals 300 and I can plug that into my equation. I can rewrite this as tangent of theta equals y divided by 300. Now this side, because this 300 is a constant, I don't have to use the quotient rule. You could, but you don't have to. I can't do that for y, though. Some of you might be saying, why did you do that for x and not for y? I can't do that for y because the derivative of that side is not 0. The only reason I can do that is because dx dt is equal to 0. If you go back and look at the first problem, you can actually do that with c as well. We said dc dt was equal to 0. If you wanted to, you could have taken c equals 26, plugged it in right from the beginning, before we even took the derivative. And this is nice because now over here I don't need to do the quotient rule. I can just use the power rule. So let's see, what do we know? I want to take the derivative of each side with respect to time, with respect to t. So the derivative of tangent of theta with respect to time, well, the derivative of tangent of theta, that is secant squared theta, is equal to, over here, y over 300. Remember that y over 300, this says the same thing as 1 over 300 times y. So that 1 over 300, that's really just a constant multiple. You can leave it as 1 over 300 times dy over dt. So okay, this is very cool. I have this relationship here. What am I trying to find? And oops, what did I forget to do? I almost forgot something here. Because the next question I was about to ask myself is, what am I trying to find? What am I trying to solve for? Well, I'm trying to solve for d theta dt, and look at what I wrote. I didn't even write d theta dt. So this side over here, it's that left-hand side that I made my error. Derivative of tangent of theta is secant squared theta. That part was correct. But I forgot that we were multiplying, or we were taking the derivative of theta with respect to time here. So we want to multiply by d theta over dt. So there's actually where my mistake was. So let's see, what am I trying to find? I am trying to find this d theta over dt. So let's do this. I'm going to rewrite secant squared theta. I don't really prefer to use secant squared theta. I'm going to write this as 1 over cosine squared theta times d theta over dt is equal to 1 over 300 times dy over dt. I'm not going to plug anything quite yet. Plug anything in quite yet here. I'm just going to try and solve for d theta over dt. Let's see, I want to get d theta over dt by itself, so I'm going to multiply both sides by cosine squared theta. And when I do that, I'll have d theta over dt is equal to 1 over 300 times dy over dt times cosine squared theta. All right, very cool. Almost there. I just need to plug in what I know. So what is d theta over dt? D theta over dt is 1 over 300. That part's fine. Times dy over dt. Dy over dt, what's that? That's 20. So times 20 times cosine squared theta. Here we might have a little bit of a problem. I don't know what theta is, and actually for this problem, I don't actually need to know it. But what I do need to know is I do need to know what is cosine of theta. What is cosine of theta? Oops, cosine of theta. I know that is the adjacent side divided by the hypotenuse. So I have the adjacent side. The adjacent side down here is just 300. I don't have this side over here. I don't have the hypotenuse. But that's okay, because I have the other two sides. I can solve for it really quickly using the Pythagorean Theorem, remembering that we're working with a right triangle. So let's see, 300 squared plus 400 squared equals c squared. Should be 9, let's see, 1, 2, 3, 4, 90,000 plus 160,000 equals c squared. I should end up with 250,000 equals c squared, so c must be 2,500. Hopefully you recognize that as a Pythagorean, oh no, I'm sorry, not 2,500, just 500. Pythagorean triple, there we go. It's moving a little too fast. So c is 500, so my cosine of theta, oops, let's do that in red up here. The adjacent side we said was 300 divided by the hypotenuse is 500. We just found that, or more simply 3 over 5. So cosine of theta is 3 over 5, so we can multiply this by 3 over 5 squared. And then at this point, we've got everything we need. So 1 over 300 times 20 times 3 over 5 squared. You could get a fraction or a decimal. It's up to you. I'm going to go ahead and get a decimal here because this video's already been pretty long. So times 3 over 5 times 3 over 5. Here I have 0.0. Oops. Let me make sure I have enough room. I will end up with 0.024. What are my units here? My units, well, the rate of change of theta. Theta is an angle. That's always going to be measured in radians. So I'm going to say radians per, what's my unit of time here? We said per second right there. So radians per second. So 0.024 radians per second. The last thing that you might want to check, hey, is that sign, does that sign make sense? We ended up with a positive. If I think about what's happening, later on my hot air balloon is going to be up here. My angle has gotten bigger. Well, that makes sense then that this is a positive 0.024 is our solution. So that seems to make sense. It looks like everything is all good here. So this is another pretty tricky one. There's a lot happening here. And again, I would just say look at as many problems as you can for related rates. I would strongly encourage you to organize your information as much as possible because it is going to make the rest of your problem easier to manage.